Okay. Okay, so in the last class we looked at the telescopic cascode, sorry, the folded cascode, right? And we found the two major advantage in the folded cascode was that its output and input common mode ranges were less coupled. Yeah. I think so, yeah. So which means you can actually put it in unity feedback and get a higher swing. And not just that, if you have an NMOS input pair, the input can be close to VDD, and similarly with the PMOS pair it can be close to ground. So it can take inputs close to either of the supplies. Okay. So these are the three reasons why you might want to use a folded cascode, right? Else you'll be better off using the normal telescopic cascode. And in the last class we started to look at a way to increase the output resistance, and the way we did was the following. We told we'll have a cascode. We observed that if this drain voltage here is held constant irrespective of the changes you have here, then this gate voltage is fixed, drain voltage is fixed, current is constant, so it acts like an ideal current source and we'll have an infinite output resistance. And we did that by, let me make some space maybe. We did that by taking this guy, we compared it with reference voltage and connected to the gate lines, right? So usual negative feedback, so we are sensing this guy because we want to fix this to some voltage. We are comparing it with respect to some reference voltage we have, and this is the node we are controlling because this gate voltage is what will set the final drain voltage here. Okay, great. So let's say now this is Vref, and I know that if this were an ideal op amp, the output resistance will tend to infinity, right? But now it looks like, I mean, if you think about it, we started off saying that we are going to build an op amp, and now it looks like we seem to require an op amp. So are we going round in circles like a baby, or is there some workaround? So what can I use in place of this now? I mean, is the question fine? So, I mean, so is it possible at all, or like, is it some hypothetical solution? I mean, in place of this, what can I use? What do you know? I mean, now can you make an op amp, some decent op amp? What are the op amps you know? Huh? I mean, this is a differential amplifier. I mean, you can start with a simple common source, diff pair, or cascode, right? I mean, of course, you can't have an ideal op amp now, but some decent op amps. So we can use those in place of an ideal op amp and see what will happen. So of course now the gain is not going to be infinity, so R out will not be infinity, right? So this is true only if let's say this gain A tends to infinity, right? So now let us see what will happen if we have a finite gain. So this is the guy. Okay, why don't you compute the output resistance, right? Assume that this has a finite gain A. I label the transistors like this, M2 and M4 as usual. Please find out what is the output resistance here when I have an op amp with a finite gain. I mean, you start by drawing the incremental equivalent and proceed, right? Okay, so please try it, but let me qualitatively get what the result might be. See, first of all, in the incremental picture, what will happen to Vref? That will be ground. Okay. So incrementally, I can say that we have a case like this. Minus A. Fine. So, I mean, now I'll try to compare it with what happens in a regular cascode. Okay, so this is M2 and M4. Incrementally, these are ground. So, if this voltage is at, say, Vx, this transistor M4 will have a current source GM-VGS, right? So, what is the current? GM4? Minus GM4 times Vx. Okay. Here, I mean, gate is ground. So, what is the same current here? If I call this as Vx, what is the gate voltage? So, what is the current then? GM-VGS. GM4 into A plus 1 times Vx. Okay. So now, I mean, one observation you can make is whatever when you had GM4, here it is replaced by A plus 1 times GM4. So here, what is the output resistance? For a regular cascode, what was the output resistance? It was GM4 R04 R02. So here again, I'll do the same thing. Wherever I have GM4, I'll replace it by A plus 1 times GM4. That's all. Fine. That is what the output resistance is going to be. Okay. So I mean, for all qualitative purposes, you can assume that this guy behaves like a transistor with a transconductance of A plus 1 times GM. So, okay, so this technique is called gain boosting or GM boosting. Okay, and have you guys seen this structure somewhere in some other circuit? Probably a slight variation with 2 resistors here. Huh? Sorry? Voltage regulators, have you guys? Voltage regulators. Okay, fine. This is, it's called a voltage regulator, so for that reason it's called a regulated cascode also. I mean, the point is, see, irrespective of whatever happens here, this voltage here is constant, right? The voltage is kind of regulated. So, this is what is used as a voltage regulator, this structure. Okay, so now this is the structure we have. I have the cascode, and for incremental purposes I just have a gain like this. Okay. So now I mean, now we'll start to replace this guy with real transistors. So here it looks like I just need to take an input, amplify it and provide it here, right? So what is the simplest amplifier we can have? Common source, right? So please help me replace it. So I have the cascode as usual. Okay, port planning. So I'm going to have a common source amplifier. I'll start with NMOS like this. I know the output I have to take from the drain. Fine? That's all. And I'll put a current source for biasing this common source here. That's all. Is that okay? So again, I'll call this M2, M4. So now what is the, this is the amplifier for us now, right? So what is minus A here? This is the input, this is the output. So let us say I label this guy M10. What is the gain this amplifier gives me now? It's a common source, right? Input is here, output is here. What is the gain? Minus GM10 or not 10? I mean, again, there is no complication. It's just a common source amplifier, only this portion, right? Okay, here it's a gate. I don't have to worry. The output is connected to a gate, so it is not going to present any impedance. That's all. Is that okay? So this is my A now. So now what is the output resistance we have? I know that R out is, oops, sorry, disappearing pen. So R out I know is going to be GM4 multiplied by the gain times R04 times R02. Okay. Again, I mean it's A plus 1, but I can approximate as A roughly. So, and A is what? GM10 R010. Okay. So now let us say I apply a increment here at the gate delta V. What will be the increment here delta V out? Let's say I apply an increment at the gate here as delta V. What will be the incremental output voltage we will have? GM of it's minus GM2 times the output resistance we had. I mean, I'm not changing anything, right? Again, if you think about it, it is the same common source amplifier, and the output resistance is this. So the current from this common source amplifier basically flows to the output resistance to generate this output voltage. GM is still the same. I have modified only the R out. So, and oops, I think I lost it again. This is minus GM2 times R out. And of course, I know what is R out. So, what is the total gain we have? I have, let's say, mod gain. Yeah, sorry, yeah, you're right, into delta V. So, this is basically, I mean, just give me the order. So, we have a GM from GM2. R out has one GM, one more GM. That here? Oh, here. Oh, yeah, okay. Yeah, thanks. Is that correct? Yeah, right. So, one more GM and 3 R naughts. Okay, so this gives the gain of the order of GM R naught cube. Is that okay? So, when we didn't have this extra amplifier, we just had a normal cascode. We had a structure like this. We'll apply delta V here, take delta V out here. Yeah, this is bothering me. Yeah. With a normal cascode, the gain, what was the gain? Yeah, it was of the order of GM R0 square. Right? So now what I have done is I have put an amplifier here. This has a gain of the order of another GM R0. So the overall gain seems to be boosted by one more GMR. Okay. So let's quickly see what happens to the swing limit, because then we could also have done this, right, to get GM R0 cube, right? But here we saw the issue was the minimum output was limited to 3 overdrives. So let's calculate what happens here. Okay. Let me redraw that. Again, I'll take the common source here. Okay. So this is M2, M4. This is say M10. So what is the minimum output I can have here? What is the okay, I mean one drain to source voltage which can be as low as 1 overdrive, and this guy, what is the minimum this voltage can go? But I mean, remember, whenever you have a gate connection, you should be careful, right? Because this guy will fix it. Because you need to make sure at least minimum of 1 gate to source voltage for this.
VGS or
exactly.
Yeah.
yeah. Let's say we call this current, I don't know, I10. So that's why I'm saying whenever you have a connection from the drain to a gate, should be careful. So let's say this is some, I want to use the same color, Ix. Okay, so minimum output will be overdrive of M4 at some current plus VGS of M10 at a current Ix. Okay. But if you didn't have
VGS of M10 is less than VGS of M2.
VGS of M10 is less than
VGS of M2.
VGS, huh? If I mean it need not be. I mean overdrive of M2 is basically a VGS minus threshold, right? Okay, this can be using this. Overdrive is basically a gate to source voltage minus a threshold. So this is, let's say, 0.1, 0.2 volt roughly. Your threshold itself will be 0.4 volt. So you can't have VGS to be less than overdrive voltage usually. I mean, your question was, can you have VGS of M10 to be less than this, right? What I'm saying is overdrive voltage will roughly be of the order of this. And you know VGS must be greater than a threshold voltage. And threshold voltage will usually be 0.4, let's say 0.5. So in practice it becomes very difficult. Unless you use some special devices which have zero threshold voltage and stuff, which will not go. Okay. So this is the minimum output we can have here. But let us say I didn't have this connection, right? I just had a normal cascode. Then what would have been my minimum output? Yeah, with a normal cascode I would have had it would have been just 2 overdrive, right? Okay, so basically we are losing a slight swing here. And if you think about it, the reason is because this NMOS here, the gate cannot take a very low input. It needs one gate to source voltage to turn on. So you cannot have an overdrive voltage and assume that this will turn on, right? But do you know some transistor which will work with a low gate input? Huh? Sorry? Yeah, I mean, if you think about, if you have a PMOS transistor, for a PMOS transistor with very low input for the gate also, it's comfortably on in saturation. So, I mean, then the suggestion is we can try to use a PMOS here. I'll be careful this time. The same thing I'm going to make using a PMOS. Okay. Okay, it's a common source. So source is at VDD for a PMOS. Input is given to the gate and output is taken from the drain. Same thing. And I'll have a bias current here. Okay. So now comfortably this can be as low as 1 overdrive voltage. Okay, so let me mark, if I call this guy VD2, or I'll call it this VG10 because it's connected to the gate of M10, and this to be VD10. Okay, so now VG10 can go as low as 1 overdrive of M2. Okay, I will not write the current for simplicity. So, and what is VD10 then? VD10 is basically this voltage. What will this be? I need to have a gate to source voltage plus this guy. Is that fine? I mean, again, we'll have some current flowing here. To have that current, you need to maintain a particular gate to source voltage. Okay, so VD10 is going to be gate to source voltage of M4 at some current plus whatever we have for the VG10. Okay. This is VG10. Okay. So now you see that the drain voltage for this PMOS seems to be greater than the gate voltage, right? I mean, this is the gate voltage, it is exceeding gate voltage by a VGS. So what can happen? Huh? This PMOS can potentially go to triode easily, right? Okay. So now look like we are stuck, right? So when we had an NMOS, we had issues with connecting the gate to a low voltage, but it had no issues in providing a high voltage to the gate of M4. Now if you look at the case with the PMOS, it had no issues in taking a lower gate voltage, but it has issues in providing a higher output to the gate, right? Okay, this is fine. The VG10 is overdrive voltage, right? That is the gate voltage for the PMOS. This is the drain voltage, right? Drain voltage is basically a gate to source voltage required plus the gate voltage itself. So the drain for the PMOS is gate plus a VGS, right? And the maximum it can go is gate plus a threshold. That's what happened. And obviously VGS will be greater than the threshold. Okay, so which means it can go into triode. I mean, for a PMOS, the drain must be much lower than the gate so that it's comfortably in saturation, right? Here the drain is at a much higher potential than its gate. So then here it can easily go into triode. Is that okay? So coming back to the problem, with NMOS, we had issues when connecting the input to a low, but it had no issues in connecting the output to a higher voltage. With the PMOS, we have the reverse problem. We don't have issues when connecting its input to a low voltage, but its output cannot be very high. So what do you suggest we can do? Yeah, but I mean, think about it, right? I mean, I don't know. This looks like, let's say you are Indian cricket captain and you find Bhuvneshwar Kumar bowls first 10 overs absolutely good, last 10 overs very bad. Let's say you have one more bowler, say Arshdeep Singh, who bowls first 10 overs very bad, last 10 overs very good. As a captain, what will you do? If you had to choose, Sorry? Same thing, right? You choose the best guy for the first 10 overs, best guy for the last 10 overs. We'll do the same thing. I mean, the other way to think is, here the problem is because both the input and output are coupled strongly by this one transistor. Do we know some other amplifier where the common modes are less coupled? Folded cascode, that's what we saw, okay? And the same thing we'll do here. So I'll first draw the normal cascode we have. Oh man. So M2, M4. We know that here what transistor I should have at the input? PMOS, because this should be at a low. Okay. Now at the output I'll have an NMOS. So what I'll do is I'll have structure like this. Okay. This is basically the folded cascode, right? I had a PMOS pair. The current coming here is buffered by this NMOS common gate and it generates the output here. So we'll say this is M10 and M12. So now you need to find, now we can find a range for VB6 and bias this guy properly so that all of them is in saturation. Okay. This is a possible solution. Okay. It's not like you'll have to use folded cascode here, but this will work better in this case. So now let's quickly find what will happen to the gain or the output resistance. So I have the same thing here. Oops, I'm getting. So here I'm going to have the folded cascode with the PMOS input pair. Okay, so this is say M10, M12, M2 and M4. Now this is my amplifier I'm putting around M4 transistors. So what is the gain here? This is where I give the input to this amplifier. This is where I take the output. What is the gain for this amplifier? Huh? It's okay to be wrong. GM of 10 into? I mean, okay, the incremental current as he mentioned is GM10. So that has to flow through this output resistance to generate the output voltage. And what is the output resistance looking down? You have a cascode structure. Okay. What is it? GM12 R012 times. That okay? Disappearing Inca. Thanks. So this is what? Please tell the output resistance. It's GM12 R012 R010. I mean, this is basically of the order of GM R0 square because we have a folded cascode put in loop, right? So now what is R out? R out of this structure is what?
Minus GM2 R out.
No, just the R out. GM4 R04 R02 times this gain. So this of the order of, I mean, or let's say let it be this. So finally we'll have to apply the delta V here and take the delta V out here. So what is the gain? GM2 times this output resistance, right? So if you have to write it, I'll have GM2 times GM4 R04 R02 times GM10 GM12. So this of the order of power 4. Okay. Again, shouldn't be surprising because with a normal cascode we will have GM R0 square. We are putting a cascode amplifier in the loop like this. This also has a gain of this. So overall gain is basically quadrupled, right? So now you seem to have stack of 4 cascodes basically, but you don't lose any swing, right? If you have to get the same gain, you will have to stack up 4 transistors like this normally, and that will basically lose you 4 overdrive voltages. But here, what is the minimum output I can go? Yeah, it's just 2 overdrive voltages, right? So here, the out minimum is, I'll just say 2 overdrive voltages. So this is the advantage if you have this gain boosting here. Great. So finally, let me just put everything in complete picture. So I have the diff pair here. Okay, I have the NMOS cascode. So around this guy, we are going to put the amplifier here, each of these guys. Okay, and this is where we are going to use a folded cascode. do this. Do this. And similarly, again at the top we'll have a PMOS structure. We'll just draw roughly here. And again, even for this PMOS, you need to have again boosting like this, right? Because both looking up and looking down, you need to have similar impedances. Okay. And okay, if I were to replace this current source, the current source here, what would I replace this by? PMOS, but PMOS normal transistor or PMOS cascode? See, because here looking down you have a cascode impedance. So looking up also should maintain the same, else you lose out the cascode, right? So here I need to have a PMOS cascode. Okay. So again, finally this guy, what will I replace it with? NMOS, but normal is fine or a cascode is needed? Normal is fine, right? Because looking up I just have one transistor, so looking down also I can just have one. Right? I mean, the reason, did everyone understand why we need to have a cascode here? This is the output resistance for this amplifier. Looking down I have a cascode. So looking up if I just have one, the output resistance will be dominated by this one guy. So there is no point in having the cascode at all. So you need to have cascode both looking up and looking down. Whereas here you see looking up you have only one transistor which gives R0. So I can just have the same here. Okay. So one last thing. So here this again has to be a similar structure like this amplifiers. So here again I'll have to use a folded cascode. So do you think the input will be an NMOS pair or a PMOS pair? Here the outputs it is sensing will be closer to VDD or closer to ground? VDD. I mean here these were close to ground and here it will be close to VDD. So no, input should be NMOS or input should be PMOS? Input should be an NMOS. Okay. This is what you do. So finally if you put everything it will look complicated, but if you understand what each of these does, it's actually pretty straightforward, right? Because essentially what you are doing is you are trying to put an amplifier in feedback like this. So, and the whole point of doing this is to boost the GM of this transistor. So, okay. So what I'll do, I'll stop here. We'll